Welcome back. So today we will move on to the second part of our combinational circuits. Today's topic is multiplexer, demultiplexer. What is multiplexer? Multiplexing means sharing. There are two types of multiplexing. One is time multiplexing, another one is a frequency multiplexing. A common example of multiplexing or sharing occurs when several peripheral devices they share a single transmission line or bus to communicate with a computer. To accomplish this sharing, each device in succession is allowed a brief time to send or receive the data. At any given time, one and only one device is using the line. This is an example of time multiplexing. Since each device is given specific time intervals to use the line, in frequency multiplexing, several devices they share a common line by transmitting at different frequencies. In a large mainframe computer, numerous users are time multiplexed to the computer in such a rapid succession that all appear to be using the computer simultaneously. Okay. So, a multiplexer or data selector, we can also call it as a data selector. It is a logic circuit that accepts several data inputs and allows only one of them at a time to get through the output. The routing of the desired data input to the output is combined by the select inputs. We can see here these are some select inputs, right? Sometimes they are also referred to as address inputs. This figure shows the functional diagram of the general multiplexer. In this diagram, the inputs are outputs. They are drawn as large arrows to indicate that they may constitute one or more signal lines. Normally, there are 2 to the power n input lines and n select lines, whose bit combinations determine which input is selected. Alright. Now, this obviously you know this is the functional diagram of the digital multiplexer. These are my data lines or data inputs. These are the select inputs. So, these select input will decide which data line will be selected and that data line will appear at the output. Okay. Now this multiplexer, it acts as a digitally controlled multi-position switch. The digital code applied to these select inputs determines which data inputs will be switched to the output. For example, the output is what I told just now. The output Z will be equal to the input D0 for some particular input code. Z will equal to D1 for some another particular code, and so on. So we can say that a multiplexer selects one out of capital N input data sources and transmits the selected data to a single output channel. This is called multiplexing. Now, here we are observing the basic 2-input multiplexer. So, you can see how many data inputs are there. 2 data inputs are there, D0 and D1, and the select line is one select line with the S. Okay. So, it connects 2 1-bit sources to a common destination, right? It has 2 input lines, one select line and one output line. This D0 and D1, these are 2 input line, S is the select line and Z is my output line. Okay. So the logic level we are applying to the select line, and it determines which AND gate to be enabled. So that is a data input passes through the OR gate to the output. Okay. This select line, it can have 2 possibilities. Either it can be 0 or it can be 1. When select line 0, this data input D0 will be selected, and that D0 will appear at the output. When select line is 1, D1 will be selected and that D1 will appear at the output. Okay. So what will be my, when S is 0, these AND gate will be enabled, and that time AND gate 2 will be disabled. Okay. So that time Z will be equals to D0. When S equals to 1, these AND gate will be disabled and these AND gate will be enabled. Okay. So in that case, Z will be equals to D1. Okay. So what will be my general output? Z will be D0 S bar plus D1 S. Okay. D0 S bar. This is the AND gate. Then D1 S, another AND operation. Then we have to put a OR gate here. Then we will get this final output. Okay. Now we will see. So a 2 input multiplexer, we have 2 input line, 1 select line and 1 output line. Okay. Now for a 4 input multiplexer, we will have 4 data line or 4 input line, 2 select line and 1 output line. And obviously we know with 2 input variables we can have 4 possible combinations, right? So these select lines, let's say this S0 is the LSB and S1 is the MSB. Okay. So with these 2 select lines we can have 4 possible input combinations, 0 0 0 1 1 0 and 1 1. So when both select line is 0, input D0 will appear at the output. That means AND gate 1 will be enabled, rest of the AND gates 2, 3, 4 will be disabled. When select line S10, S0, 1, then D1 will appear at the output. That means this second AND gate will be enabled and rest of 1, 3, 4 will be disabled. Likewise, for 1, 0, this D2 will be appearing at the output, AND gate 3 will be enabled, rest of the AND gate will be disabled. And for both the select lines, when it is 1, D3 will appear at the output and AND gate 4 will be enabled and rest of the AND gates will be disabled, right? So if we express it in terms of the output, what will be my final output Z here? S1 bar, S0 bar, D0 plus S1 bar, S0, D1 plus S1, S0 bar, D2 plus S1, S0, D3. So these entire output expression, if we put it in terms of the logic gates, so D0, S1 bar, S0 bar, this will give us, this is the first case, right, for first term. Then for each term, this is my D1, then S1 bar, this is S0, this is S0, this is for the second term, then D3, then S1, this is S1 and S0 bar, this is my third term, and D2, right? And for the fourth one, we will have D3 into S1 and S0. All these AND gates output, we have to put it in a OR gate, right? Then we will get the final output. Okay. Now, for the 8 input multiplexer, what we will have? For the 4 input multiplexer, we had 4 input line, 2 select line and 1 output. For 8 input multiplexer, what we will have? We will have 8 input line, 3 select line, 2 cube. 2 cube is 8. So 8 input line will be there, 3 select line will be there, 1 output line will be there. And for 3 variables, we know 8 combinations are possible. So this is S2, S1, S0. Let's consider S0 as the LSB. So let's write all the possible 8 combinations starting from 0 to 7. Okay, 0 to 7. So when all the select line is 0, this D0 will be coming at the output, right? When 001, D1 will be selected. When 010, D2 will be selected. Then 011, D3 will be selected. 100, D4 will be selected. 101, D5 will be selected. 110, D6 will be selected. 111, D7 will be selected. Right? Now, let's move on to the next part. It is possible to realize the higher order multiplexers with lower order multiplexers. That means we can realize 8 input multiplexers using 4 input multiplexers. Okay. Okay. How can we realize the 8 input multiplexer using the 4 input multiplexer? We need 2 4:1 marks. We need 2 4x1 marks for it, right? So each 4x1 marks will have 4 input line to select line. Again, second 4x1 marks will also be having 4 input line and 2 select line. So now for the first and the second 4x1 marks, we can write the select line S1 and S0. This is my final 8x1 marks. D0 to D3 input lines or data lines we can give as the first 4x1 marks input lines, and D4 to D7 we can give as the second data line for the data lines for the second 4x1 marks. Okay. Now we need another 2x marks here, because 4x1 marks, first 4x1 marks will be having one output, second 4x1 marks will be having one output, right? Now which output will be selected, that will be decided by these S2, right? So we need another 2x marks over here. So when S2 is 0, D0 will be selected. When S2 is 1, D1 will be selected, and it will give you the final output. So starting from the LSB, we have to connect the first 2 selection line to the both multiplexers. That is why we have connected this S1 and S0. Same we have kept for both 2x1 multiplexer. Okay. Now, to select any one of the output from these 2 multiplexers, we require one more multiplexer, right? So in this case, that is why we are using this 2x1 multiplexer to select any one of the 2 outputs coming from these 2 4x1 multiplexer. And the selection line S2, it is connected to this 2x1 multiplexer. Okay. Now, we can also realize 8x1 marks using 2x1 marks. So for that we need 4 2x1 marks. Okay. Each 2x1 marks is having 2 input line and 1 select line. This is my final 8x1 marks, right? So 8x1 marks is having how many select line? 3 select lines, right? So S0 is the LSB of the select line. So let's take this S0 select line for all these 4 2x1 multiplexer. Okay. So for the first multiplexer, this let's give this D0 D1 as data line. Second, let's give D2 D3 as data line. For third, let's give D4 D5 as a data line. For the fourth one, let's give D6 D7 as a data line. So for each multiplexer, the outputs are coming. Now which output will be selected, that will be decided by this 4x1 marks. And for this 4x1 marks, the select lines will be keeping here S2 and S1. Okay. So here 4 input combinations are possible for the select line. When both are 0, D0 will be selected, right? 0, 1, S2, 0, S1, 1, D1 will be selected. Then S1, 1, S2, 1, S1, 0, D2 will be selected and both 1, D3 will be selected, right? In this way, we will get the final 8 cross 1 marks using the 2 cross 1 marks, okay? Now, it is also possible to realize the 16 cross 1 marks using the 4 cross 1 marks, okay? How we will get the 16 cross 1 marks? For 16 cross 1 marks, 2 to the power 4, right? That is 16. So, for 2 to the power 4, if it is 16, for a 16 cross 1 marks, we will have 4 select line and 16 input line. So, we need 4 cross marks here. 4 cross 1 marks. Let's say the 4 select line of the 16 cross 1 marks are starting from the MSB to LSB is S3, S2, S1 and S0. Now, let's take the 2 right, starting from the right side, the LSB. S1 and S0 select line, that is, take that S1 and S0 select line and put it for all the 4 cross 1 multiplexer, okay? Now, for the first 4 cross 1 multiplexer, there are 4 inputs, D0 to D3. For the second 4 cross 1 multiplexer, 4 inputs will be D4 to D7. For the third 4 cross 1 multiplexer, the inputs will be D8 to D11. And for the fourth 4 cross 1 multiplexer, the inputs will be D12 to D15. Right? Now, we need another 4 cross 1 marks over here. So, rest of the 2 select line S3 and S2 will put at 0. So, when both will be 0, D0 will be selected. When this is 0, this is 1, D1 will be selected. When S3 1, S2 0, D2 will be selected and both are 1, then D3 will be selected. Thus, we can realize a 16 input marks using a 4 input marks. Now, it is also possible to realize the Boolean function or to implement the Boolean function using the multiplexer. Okay. So, suppose we are given this function f, which is a function of, it is a 3 variable function a, b and c. And this is the min term. What are the min terms? 0, 2, 3 and 7. So, it is a 3 variable function. Obviously, 8 input combinations are possible. Let's first write the truth table with 3 input variables starting from the 0 to 7. Let's write all the combinations. Okay. Now, for these 0, 2, 3 and 7, for these min terms, the output will be 1. So, for 0, output will be 1, 2, output will be 1, 3, output will be 1 and 4, output will be 1. So, it is already, since it is given the 3 variable function, so we know in 8 cross 1 multiplexer we need over here, because in 8 cross 1 multiplexer only we can have the 8 input combinations. Okay, so we have the 3 select lines in 8 cross 1 marks. So these select lines we will put it over here. This is ABC. C is my least significant bit. So this is my D0, D1, D2, D3, D4, D5, D6, D7 like that. So D0 is already 1. Okay. Then D1 0, D2 1, D3 1, D4 0, D5 0, D6 0, D7 is also 1. Okay. So this is my final output. Okay. So when all 3 select line are 0, this 1 will appear at the output. When 0 0 1, 0 will appear at the output. When 0 1 0, 1 will, this 1 will appear at the output, like that. Okay. Now let's consider another example. Another Boolean function implementation using the multiplexer. Let's say this is my Boolean function f a b c, which is the min term of 1, 3, 5 and 6. Now these Boolean function, previously it was like not specified. We can use any multiplexer to use that. But here let's say it is specified. We have to use a 4 cross 1 multiplexer only to realize this Boolean function. So how to realize these function using a 4x1 multiplexer. So here you can see three variables ABC, right? So this is a 4x1 multiplexer, right? We have 4 input line or data line D0, D1, D2, D3, 2 select line and 1 output. Let's take B and C are 2 select line of this 4x1 multiplexer, and A, let's take an input line or data line. So for 3 variable function, first we will make the truth table. We can have 8 possible combinations, right? Starting from 0, 0, 0, 0, 0, 0 to 1, 1, 1, right? Now, so for one min term 1, 3, 5 and 6, my output will be 1. So 1, 3, 5 and 6 output will be 1, right? So now we will make one table, one implementation table. So while doing the Carnot map, we have seen for a 3 variable function, we must have the 8 cells. So we will have the 8 cells, 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now, at the top of the implementation table, we will write all these input data lines, D0, D1, D2, D3. Then we will number it, 0, 1, 2, 3, 4, 5, 6, 7. Now, if you notice in the truth table, here or here from this is 0, this is 0, this is 0. So for the first 4, A is 0. And for the second 4, A is 1. So from 0 to 3, A is 0. So we can from 0 to 3, for the corresponding row of 0 to 3, we can put A0 or A bar, right? And from 4 to 7, A is 1. So 4 to 7, 4, 5, 6, 7, A is 1. So we can simply write it as A, right? Now, for these 1, 3, 5 and 6 min terms, output is 1. So we have to circle it, 1, 3, 5 and 6. Now we have to look each column. If for the first column, we don't have any circle, right? We will simply put it at 0. For the second column, both circles are there. We will put it as 1. For the third column, this 6 is circled and it corresponds to A. So we will write it A here. And for the last column, 3 is circled and it corresponds to A bar. So we will write A bar over here. Now, this is a 4x1 marks, D0, G1, D2, D3. These are 4 inputs. B and C, these are my select lines, right? So, D0 is 0, D1 is 1, D2 is A and D3 is A bar, right? F is my final output. So, when both are 0, this D0 will come at the output. When B0, C1, D1 will come at the output. When B1, C0, D2 will come at the output. When both are 1, this D3 will come at the output. Now, here there is another terminal which is called the active low enable. Active low enable means when if it is 0, that means your multiplexer is enabled. Okay. And if it is 1, that means your multiplexer is disabled. Okay. Now, let's start the demultiplexer. Okay, what is a demultiplexer or data distributor? So, a multiplexer, it takes several inputs and transmits one of them to the output. Now, what does a demultiplexer do? A demultiplexer performs the reverse operation of the multiplexer. It takes a single input and distributes it over several outputs. So a demultiplexer can be thought of a distributor since it transmits the same data to different destinations. Thus, whereas multiplexer is an n-to-1 device, a demultiplexer we can consider it as 1 to n or 2 to the power n device. So this figure, what you are observing here, it shows the functional diagram for a demultiplexer. The large arrows for the input and the output, they can represent one or more lines. The select input over here, it determines which output line, determines the output line to which your input data will be transmitted. Okay. In other words, the demultiplexer takes one input data source and selectively distributes it to 1 to n output channels, just like a multi-position switch. Okay. So now in this figure we are having, this is just the reverse of your multiplexer. We are having a 4 to 1 demultiplexer. We have one input line, 2 select line and 4 output lines. So this is the truth table of this 1 to 4 demultiplexer, and this is the logic symbol. A 1 to 4 demultiplexer, it has single output D in 4 outputs. This demultiplexer, this 1 to 4 demultiplexer, it has only one input D in, 4 outputs Y0 to Y3 and 2 select inputs, right, which are here S1 and S0. The input variable D in, it has a path to all 4 outputs. But the output information is directed to only one of the output lines. The truth table is here. You can see here. So when here enable line is, because it is not active low enable, when enable line is 0, so we don't have any combination for the select line and input line, so output will be 0. Okay, so you can see from this truth table, when all the enables are 1, then only this multiplexer is working, right? So when you can see with 2 select lines, we can have 4 input combinations. So we have written each input combinations 2 times, 0, 0 2 times, 0, 1 2 times, 0, 1 0 2 times, 1 1 2 times. Because for we have written each select line combination 2 times. Because for each select line combination, the D in input can either be 0 and 1. For 0 0, D in can be either 0 or 1. For 0 1, D in can be either 0 or 1. And for 1 0, D in can be either 0 or 1. For 1 1, D in can be either 0 or 1. Okay. So from the truth table, you can see that it is clear that the data input D in is connected to the output Y0 when your S1 is 0 and S0 is also 0. The data input is connected to output Y1 when S1 0 and S0 is 1, right? Similarly, the data input is connected to output Y2 when S1 1 and S0 is 0. And when both are 1, then what happens? The output is connected to Y3, right? So if you express it in terms of the logic symbol, what you will get if you express it in terms of the logic symbol? So Y0, how you are getting the Y0? How you are getting the Y0? D in Y0 1 for what input combination? D in into S1 bar S0 bar. That's what you are doing, right? Y1 is 1 for which input combination? D in into Y1 is 1 for which input combination? You can see over here Y1 is 1 for D in into S0 into S1 bar, right? This is S1 line, this is S1 bar line. This is S0 line, this is S2 bar line. Then Y2 is 1 for which input combination? D in into S0 bar into S1. Y3 is 1 for all the three D in into S0 into S1, right? So obviously Y0 will be S1 bar D is S0 bar D in Y1, S1 bar S0 D in Y2 equals to S1 S0 bar D in, and Y3 is S1 S0 in D in. Okay. Now we will see the 1 to 8 demultiplexer. So 1 to 8 demultiplexer has 1 input data D in and 8 outputs Y0 to Y7 and 3 select inputs S2, S1 and S0. And it distributes 1 input line to 8 output lines based on the select input lines. Okay, so the truth table of these 1 to 8 demultiplexer is shown over here. Okay, so same for 3 variables we can have possible 8 possible combinations S2, S1, S0. It can be starting from 000 to 111, right? And this multiplexer will be working when the input is 1. All the D input is 1, right? So for first we have to check that when D in 1 and all the select line is 0, output will be 1. When this is 001, this Y1 will be 1. When 010, out Y2 will be 1. Then 100, Y3 will be 1. Then 110, Y110, this Y3 will be 1. For 010, Y2 will be 1, and for 011, Y3 will be 1. For 100, Y4 will be 1. For 101, Y5 will be 1. For 110, Y6 will be 1. For 111, Y7 will be 1. So that's what we have to realize with this logic circuit. So Y0 means what? Just see this entire row. Y0 means D in into S2 bar into S1 bar into S0 bar, right? Y1 means what? D in into S2 bar into S1 bar into S0, right? Y2 means what? S2 bar into S1 into S0 bar, right? Then Y3 means what? S0 bar into S1 into S2, right? Y4 means what? S D in into S2 into S1 bar into S0 bar. D in will be multiplied with each term. Okay. Then Y5 will be 1 for D in into S2 into S1 bar into S0. Then Y6 will be D in into S2 into S1 into S0 bar, and Y7 will be equals to D in into S2 into S1 into S0. So we have all the terms of the output. We can simply use this logic gates to realize the outputs. So first you make a line for D in, then you make a line for S2, and this NOT gate is for S2 bar. Then this line is for S1, this NOT gate is for S1 bar. Then this is the S0 line, and this NOT gate is for S0 bar. Then you just insert all these input to all this. We need the 4 input NAND gates, right? We need 1, 2, 3, 4, 5, 6, 7, 8. We need 8 4 input AND gates to realize each output Y0 to Y7. So that will give us the 1 to 8 demultiplexer. Now, if we want to realize the 1 to 8 demultiplexer using two 1 to 4 demultiplexer, what we will do? In 1 to 4 demultiplexer, we need two 1 to 4 demultiplexer. Okay. So 1 to 4 demultiplexer will be having two select line. So these two select line we will join together. Okay. And we have one D in will be the input. D in will be the input for the both multiplexer. So this is the D in of the first multiplexer. This is the D in of the second multiplexer. Okay. Now this is my one enable input. So these enable input, let's give the direct enable to the second multiplexer and invert it to the first multiplexer. Okay. So the operation will be the same way we have realized here. 1 is to 4 demultiplexer. What we had here, 1 input line, 2 select line, 4 output line. So for each and every one of these multiplexer, we have to first form a truth table. Then we need to decide the output combinations. Then by using these logic symbols, we have to check whether we are getting the 1:8 demultiplexer or not.